Okay, and I hope that I'm getting some slides with some notes
Yeah.
on for the next. So Laura is the project manager for Aurorasaurus. So those of you who really were into dinosaurs, this is your big chance to see a dinosaur picture on the slide. She has a BA in history from College of William and Mary, and then she decided to learn about museum education, which is a really interesting career path that hopefully she'll mention to us a little bit. She's worked at all sorts of cool places like the National Archives Foundation and the National Air and Space Museum, which is one of my favorite museums that I always visit anytime I'm into DC. And I don't know how many of you have heard of the iNaturalist app, but it's actually an app and you can use it in your own outdoors. I've learned a little bit about it. And so, inspired by Aurora, seen in Iceland, she's going to tell us all about this really great citizen science project that hopefully some of you will get involved in. So take it away, Laura.
Let me just get my screen share going. I think I need, yeah, there we go. Okay. Oh, hang on. It moved everything. All right, there we go. Okay. So, hi everyone. My name is Laura Brandt Edson. I'm the project manager for Aurorasaurus, which is a participatory science project, also called a citizen science project, with NASA and the New Mexico Consortium. We're funded by NASA and NSF. So I just want to give you a little bit of structure for what I'm going to talk about today, because I'm an ADHDer and I can talk forever, but this is your time and I want to make sure that I'm talking about what you want to talk about. So I'll talk a little bit more about me and my career path. We'll talk a little bit about you using the chat. We'll talk about what participatory science and citizen science is. We'll talk a little bit about Aurora science and how auroras happen. I think you may have had a presentation on that originally, but we'll kind of review a little bit of that and go a little deeper. And then we'll talk about Aurorasaurus and some resources that we have that you could learn more about. So I see some great suggestions coming into the chat already. Please let me know in the chat what you would like to hear about. What are things that you're curious about? What are things that you're interested in? What do you want to learn? I'll give you a minute to that. I'll talk about the May 10th Aurora. That was so cool. I got so excited. I saw the Aurora from Washington, D.C., which is unheard of. So that one's very exciting. And Braden, you saw it as well. That's fantastic. I love it. All right. So a little bit about me. Again, I'm the project manager for Aurorasaurus. That means that a lot of what I do is volunteer coordination, and with my museum education background, a lot of what I do is translating resources for the general public. My favorite part of Aurora chasing is the connecting with nature part. It's really fun. I get so excited about getting other people excited about things, and that's where my career path has taken me. I graduated undergrad in 2008, which was a very interesting time to come out of college. And I graduated with a history degree, and I went, I'm going to be a museum interpreter, and it's going to be great. That didn't work out. So I went into fundraising and marketing for a couple of years at the National Archives Foundation. And what I found out there was that the thing that I loved the most was National History Day. And I don't know, has anybody here participated in National History Day, either in middle school or high school? No, that's all right. It's pretty cool, but not every school does it. So, so I just got so excited about getting other people excited about history, and decided to go back to school and get a museum education degree, which is a degree in how to teach, how to educate. It's not necessarily subject locked. So then I ended up working at a couple of different museums on very different subject matter, and then ended up coming adjacent here. So I think the best advice I can give career-wise is be open to possibilities. Um, your career will take you places that you don't expect. If you had told me 10 years ago, 5 years ago that I would have been at NASA, I would have been like, what are you talking about? But here I am. And I'm here as a non-scientist with a lot of other people at NASA who are non-scientists, as I'm sure you learned last time. I have a lot of different interests, and some of those apply to what I'm going to show you today. Anything you do will apply to your job at some point. That is the thing that I have learned. All right. So now that you've heard a little bit about me, I'd like to know a little bit about you. You can use the chat for this or raise hand function. Give me a thumbs up in the chat, whatever you like to do. If you've seen Aurora before, I know we had at least one person who's seen Aurora. Is anybody else? Pictures, but not live. Yeah. Yeah. We'll talk a little bit about how that's a very different experience. And it's both of them are equally cool, but they are really different. All right. Nothing but the May 10. Yeah. It's challenging in a lot of parts of the country. Oh no. Oh, every Aurora chaser knows what it is to sleep through an Aurora. That is, you are with the community there. Everyone knows that pain. Where was I on May 10th? I was standing on the back deck of my apartment, looking at the sky with my phone going, is it there? Is it there now? Is it there now? So, yeah. All right. Raise your hand if you've encountered participatory science before. Has anybody done participatory science? I not. Anything else? That's okay. Cool. We have newbies. That's exciting. Um, that is always, oh, we've reported earthquakes online. Megan has reported earthquakes. Gabriel's done a little bit of iWire, Galaxy Zoo, and iNat. Love it. And we have a lot of new folks, and that's awesome because you can join at any time. And I love it. Observe light pollution. Fantastic. Has anybody done Aurora participatory science? And it's okay if it's no, I won't be offended. Yeah, that's all right. We have a new over here. That's fantastic. So it's always an opportunity to try something new. Now, raise your hand or give me a thumbs up in the chat if you love nature. Yeah, absolutely. A lot of us do. Raise your hand if you think helping with scientific research sounds fun. We've got more hands raised. Fantastic. Yeah, I think so too. That's one of my favorite parts of all of this. So you've got what it takes to be a participatory scientist, excuse me. And fundamentally, what it comes down to is participatory science is about falling in love with the world more. It's people who are not professional scientists in that field of study contributing to scientific inquiry. So I do a lot of participatory science with Aurorasaurus. I do it with iNaturalist. I have found it very meditative to do penguin watch, which is looking at pictures and counting penguins. I really enjoy that. Some people gather data like I tend to do. Some people analyze data. I know we have a lot of interest in data analysis in this group. Some people do independent research and some lead projects on their own. There's a whole slate of things that you can do. And one of the places that you can find projects that match your interests is SciStarter. We are listed there. The NASA projects are listed there. It's a really great kind of catalog of places that you can find really, really fun stuff to do. So let's shift gears a little bit. And we'll talk a little bit about what is Aurora. And I'm looking back through the chat. I know we have a lot of questions about Aurora and its effects. And I'll go into a little bit of that. Again, I'm not a scientist, so if you have a question that I can't answer, what I'll do is write that down, and then I'll go ask the scientist that I know, and I will email in to share with you later. All right, so we have the Northern Lights, the Aurora Borealis, and the Southern Lights, the Aurora Australis. A lot of times they're relatively symmetrical because the same processes drive both of them. And they are made by processes in the space between the sun and the earth, as well as in the earth's upper atmosphere. Uh, excuse me, I must have misspoken. Australis is in the south, Borealis is in the north. So Aurora Borealis, northern lights, Aurora Australis, southern lights. And they do see them in Australia, so I always think that's fun. I'm going to show you a really quick video for the sake of brevity about the processes that make this happen. We make that joke a lot. The sun is our nearest star. It is constantly giving off particles along with magnetic fields that flow out across the solar system. Scientists call this the solar wind. As the solar wind reaches Earth, it draws the magnetic field around Earth out long, away from the sun. Charged particles from the solar wind get stuck in these magnetic fields and go around to the far side, like this. There, they stretch the magnetic fields out, and snap! The magnetic fields reconnect with one another in a new way. The particles are accelerated back toward the north and south poles, where they rain into the ionized upper atmosphere. They collide with atoms and molecules there to create the lights of the aurora. So the big takeaway from that video is that a lot of times in the news, what you'll see is talk about particles going in directly at the poles. And that's not quite right. There is a kind of aurora that's made that way, but it's not the kind that our eyes can see. The kind that we watch at night is made from this reconnection on the opposite side of the sun in what we call the magnetotail, as that magnetic field flows away from the sun. So that accelerates particles back towards the poles, and those come down into the upper atmosphere. When they do, they basically ricochet off of particles. I don't know if anybody here has ever played Plinko, a game before, but it's a little bit like that, where it bounces off one, then it bounces off another, all the way down until it runs out of energy. And when those particles give that energy to the atoms and molecules in the upper atmosphere, the atoms and molecules get so much energy they don't really know what to do with it, so they let it out as light. Different atoms and molecules hit in different ways at different altitudes, create different colors of light. So this is a really important clue. Just from looking at a photo of aurora, you can actually get scientific information from it, which is one of the reasons that we like to collect photos. Come on, there we go. So we have at the highest altitudes, oxygen making red colors. Below that, we have oxygen making green, which is the most common color in the aurora, as well as a little bit of nitrogen blue. And in different storms, you'll see some of those combinations. And then sometimes in a really, really strong storm, if the particles have enough energy to make it all the way down, you'll see a little pink border on the bottom of the aurora, and that's also nitrogen. But it tells us what the altitude is, and it tells us what the composition is. Pranav, you have a fantastic question. How is that light even visible? Yeah, it's these tiny little particles, that tiny little photons coming off of atoms and molecules, but there's so many of them. It's like glitter, where it's just bits of light shimmering in the darkness, outlining the magnetic field lines that surround our planet. And so all of them together are visible. But the challenge is that light pollution often washes it out because it's not always super, super bright. And we'll talk a little bit about that too. One of the things that I like to do is I like to do fiber arts. I don't know if anybody over here likes to knit or crochet, but this hat that I made up the other day gave me kind of a sense of how big the aurora is. So if we take each row of knitting as 6 miles of altitude, down here at the very, very bottom, this row 1, that's the highest airplanes, and that's where Mount Everest is. Row 2 here, highest clouds. We've got low Earth orbit starting sort of in the middle of the green aurora. And the International Space Station is going through the red aurora. So this is really huge, the aurora that we are looking at night. All right. And thank you, Lynn, for jumping in with some answers to the questions. Okay, so we tend to look at auroras and people see all kinds of shapes in them because they're so dynamic and they're so beautiful and there's so much going on and they look different at different angles. But we tend to categorize into three different shapes of aurora. Discrete arcs, which are those ribbon-like ones that you usually see in photographs. Diffuse glows, which are sort of like just very still, blobby kind of glows on the horizon. And then pulsating patches happen closer to morning, where the aurora will literally start blinking like a disco show, and it's really cool. And there's a lot of really, really interesting physics that goes into that. We also have a phenomena that are similar to auroras. You could colloquially call them auroras, but they happen more towards the equator than the actual aurora itself. One of these is named Steve. And Steve was brought to the attention of scientists by aurora photographers, by people who are just interested in aurora, live beneath it, photograph it, observe it all the time. And Steve is really, really cool and has started this whole field of study where people are now experts in Steve's science. The aurora chasers from Alberta who worked with Aurorasaurus and other scientists to write the first modern paper about Steve, called it Steve after the film Over the Hedge, where the characters see a hedge and they're like, what is that? It's kind of scary. We don't know what it is. Let's name it Steve, and then it won't be scary anymore. So that's why it's Steve. It was then backronymed, which is when you give an acronym to a word that already exists. And it became strong thermal emission velocity enhancement. Gabriel, that is a great question. What makes Steve different from other auroras? Steve happens more towards the equator. It does not, as far as I understand, have to do with the same kind of particles falling down, but it has to do with strong flows in the material at that latitude. And I do have a blog post about that I can share with you all later. But it is really, really cool. Its spectrum is also different. So when people look through special lenses that can separate out the light that's coming from the aurora, the regular aurora has its own signature wavelengths, and Steve has different ones, which are really, really, really neat. So with that in mind, we talked a little bit about color. We've talked a little bit about altitude. What are some thoughts that you have about this aurora? This is an observation that was made last week by our friend Astro Bob, who is one of our Aurorasaurus ambassadors. And his observation is this second from the top that's circled in yellow. It's a little plus sign. And he gave us a picture. So based on this observation, what are some things that you noticed about Bob's observation? Pink lines, yeah. It was near the border, the Minnesota-Wisconsin border. It seems pretty static. Yeah, it was static in the picture that he took. We don't know how much it was moving just from that photo, but we do see those pink lines, and you can see that those are at the top. So we're looking at that oxygen red aurora up at the top there. One of the things that can happen, it's a little bit challenging. You see how there's almost more yellow than green? One of the things that complicates it is that light also mixes a little bit differently from paint. So when you have green and red aurora, they can mix to yellow. When you have red and blue aurora, they can mix to pink. And when you have the green and blue together, they can almost look teal. So it's kind of cerulean color. Yeah. So You have a lot of cool things that you guys can tell from that, and you can look at that and see the altitude and the composition. We can say that this is a very oxygen heavy aurora here. Yeah. So we did have some questions about May 10th, and a really, really cool thing happened on May 10th, where enough energy was sent from the sun in the form of a whole slew of coronal mass ejections, which are matter and magnetism, very importantly magnetism, that come off the sun very, very fast and very, very hard. And they all kind of squish together like bumper cars and push themselves into our magnetic system. And we got a geomagnetic storm triggered, which is the process that it's very, very complicated, but it is effectively the storm, the aurora storm that happens when you have a tremendous amount of energy coming into the system like that. So this is the Aurora Source website during that time, and you can see people reporting. It looks very much like the aurora is moving overhead. What you can see there is a model called Ovation Prime, which somebody asked earlier about, can we see a map with an approximation of where the aurora is visible? That's exactly what Ovation Prime does. Is it infers, it predicts where the aurora is going to be visible. And you'll see there's a little red line, and that is the view line. So that's where they think that it may be visible. We take reports and we ground truth that. So we say, okay, great. So the model says this. How do we find evidence to improve that? Well, we ask people from the ground to look up, take pictures, tell us if they saw it there, and then we compare the sightings with the model, and then we can tweak the model to make it more accurate. So that's a lot of what we do. And you can see here that the model was that the aurora was visible a long way away from where it usually is, which is in an oval around the magnetic north and south poles up in like northern Canada. It came way down as the earth rotated underneath it. And we saw aurora. And I think a couple of people said that you saw aurora on May 10th through 11th, which is fantastic. I saw it somehow in Washington, D.C., which is very, very light polluted. But it was tremendously exciting. We got lots and lots of reports. These are places that do not frequently see aurora, where the magnetic pole is right now. It wanders around. So historically, they would have. Langhorne, Pennsylvania is more light polluted than DC. That is a thing that happens. It is unfortunate. And it does wash out the aurora because that beautiful light coming from those tiny little particles is not always super bright. And it can be washed out by ambient light, by the moon, by light pollution, all of the things. Clouds can also block the aurora because they're in front of it. And weather can create problems for going out. So yeah, if it was clouds, that would have blocked it as well. All right, so the question that we always get is, how can I see the aurora? And I do have to preface this with, if you are a minor, definitely take an adult with you. If you're an adult, it's also really great to take other people with you. It's always safer to be out at night in groups. But basically you want to be in a part of the world underneath the auroral oval to maximize your chances, because seeing the aurora is always a game of chance. You want to go during a time of the year when the sky gets dark enough to see it. Find a place with a clear view towards your nearest pole, and in the northern hemisphere, that's the North Pole. You want to watch weather forecasts. You want to basically, yes, find a dark sky national park. We love those. They're fantastic. When you see the aurora, it might look different to your eyes than to cameras. That doesn't have to do with the aurora so much as it has to do with the biology of our eyes. So our rods and cones take in different kinds of light. Our cones, which see color, cells in our eyes, have to have a certain threshold of light before they are activated. Otherwise, we see in dim light and black and white. And that is why the aurora can look different. I do have a pro tip from a Aurora guide, Andy Whitteman, who is a friend of ours, which is if you shine a flashlight on your nose, not in your eyes, but on your nose, below your nose, it'll give your eyes just enough light to activate those cones for a little bit and see the aurora colors. It will ruin your dark vision though. Different cameras can see infrared and ultraviolet. People actually hack cameras to see different wavelengths for astrophotography, which is very, very cool. So auroras can tell us the conditions in near space, space weather. We talked about a little bit about space weather effects. You all were asking about the ground effects that can happen. Those can happen. They're really, really rare. And part of the reason that space weather forecasting as a field exists is to give people the information that they need ahead of time to put satellites and electric grids and so on in safe mode. But very importantly, we're talking about very, very large systems. The aurora can't affect your cell phone. It's too small. Or your laptop, also too small. But they also, give us a lot of information about the world around us and about our magnetic field. What are some other science questions we can ask? There's still a lot of mysteries about how the aurora works. So if you want to come hang out with us in heliophysics, you might be one of the people to figure those out because we're still figuring things out. And can the data over time help us predict solar storms? Solar storms are very, very tricky to predict for a lot of reasons, mostly because there's 93 million miles between the sun and the earth, and a lot can happen in that time. Auroras CMEs and fast solar wind, which are the things that tend to create auroras, coming off of the sun can run into traffic and slow down, or they can speed up. Lots of things can happen, and it's hard to know in that interim there. So Aurorasaurus, we project that model in the view line. People make reports. We used to crowdsource reports from Twitter. We are no longer able to do that. But that science eventually becomes data that can be analyzed. And we clean our data before it's published, but we publish it to a public repository called, open source repository called Zenodo. So if you want to look at our data, you're welcome to. And again, this is what that looks like on a really, really good night. This was the most reports we had ever had in one night. It was 5,000 reports. People got really, really excited. We also have other resources. This is a very cool graph that shows how likely aurora is to be visible in about an hour's time at your local time. So green at the very bottom is like, meh. Yellow and orange, yes, we're getting somewhere. Red, let's go look. You can see that this one kind of broke the chart a little bit, which is great. You always get excited about those. It surpassed the red into a place above the grid there. We love people who take photos, and it's really important to get a color photo at the right time with good phenomena in it. One of the things that I do is write blog posts that go into in depth a lot of these topics that y'all are talking about. I'll put the URL for that in the chat right now, so you can take a look at that. We also have a Learn page that gives some really basic information if you're looking to explain this to other folks. And we do create activities. A lot of these are kind of aimed at middle schoolers, but if you're working on a school project to share with friends or siblings, or if you're doing mentorship for younger folks, we have a number of resources, including a 3D print of the Earth's magnetic field, a virtual tour, and a really fun card game that explains how to see aurora. So thank you so much. Sped through that really quickly, but please feel free to ask me any questions. Again, if I can't answer them, I will find out from somebody who can and get back to you.
All right, let's give a thank you to Laura for this amazing talk.
It was just great.
You're amazing talk, Laura.
Thank you.
Yeah, beautiful photographs. I wish I could just like move to Alaska or Iceland or someplace, but we'll just keep rooting for a really big solar storm so we
Oh,
get a chance in California.
It's one of those fascinating things where aurora chasers always want really big storms and industries are like,
Oh, we don't want storms.
so there's a lot of different interests there.
Yeah, maybe you could say a few words about the internet and the effects on the internet, because people had questions about that earlier.
That is a question that I don't know how to answer. So I know that it can have effects on large systems like power grids. And the reason it has to be large is because the Earth's magnetic field is not very strong. Earth's magnetic field is about the same strength as a fridge magnet. It's just very, very large. So if a fridge magnet's not going to damage your phone, you know, the CME is not going to damage your phone. But the internet specifically, I don't know about. So that's a question that I can ask around and get an answer and get back to you.
I think I know what my answer would be, which is
Yeah.
that a lot of the internet uses satellites now to get to different places. And so it's the satellites that are up there that are most likely to be affected by the particles and the energies, you know, radiation energy sent out by the sun when it has a big flare or coronal mass ejection. And so you're worried about the effects on the satellites because it only takes one, you know, well-aimed cosmic ray to make your satellite go into safe mode or have a fault or something like that. So, you know, I think most of the people that were worried about this, you know, the internet were using satellite-based internet. But if you were using cables that were under the ground kind of internet, I don't think you're going to have any effects unless those cables are fed by satellites.
Yeah. So there are a couple of things that can happen with satellites. And again, this is not my wheelhouse, so I'll just say the little bit that I know. And if there are deeper questions, I can, you know, Lynn can either explain it or I can ask and find out for you. But I do know that one of the reasons that space weather forecasting exists is to let people with satellites know that they need to get their satellites into safe mode before the space weather hits. And the nice thing is that because it is 93 million miles and CMEs do not travel at the speed of light, we have usually a couple of days notice before a coronal mass ejection, that kind of ball of particles and magnetism gets here. So there's time between when it's observed coming off of the sun and when it gets here for people to put stuff in safe mode. I also know that it can change the density of the ionized part of the atmosphere, the ionosphere, which can affect radio and can also make it create more friction for some satellites in lower orbits. And that can affect satellites. There were some famous cases of that over the past year.
Yeah, and the satellite that I did my PhD thesis on re-entered in 1979 when there was a huge solar flare back during 2 solar maxes ago, at least.
Yeah.
And it's the direct result of the atmosphere puffing up as it gets all the extra energy from the sun during the solar maximum period. Right, the atmosphere expands. The satellites that used to be above the atmosphere are now flying through the atmosphere, so they get a lot of drag, and then they all start tumbling down. And that killed my poor SAS-3 satellite in April of 1979. It was a very sad day, and I remember it.
That is heartbreaking
now, because that was the satellite my PhD thesis data came from.
You know, and this is the thing, is that we, you know, as we've learned more since the 70s, we've been able to create systems that are a little bit more resilient. But it's important to create those systems, and it's important for us as we generate new technologies to be aware of the ways that the sun can affect technology. Solar maximum before the advent of satellites was not a big deal. The Earth, you know, the sun can't hurt us. So, you know, we just didn't think about it. It just didn't affect the world. But with electrical technology, with telegraph technology into phone lines and into satellites, it's become more and more susceptible. Let's see. Yeah, Lynn, I'll let you explain safe mode because that is beyond the scope of my knowledge.
Yeah, so all NASA satellites are designed to have a safe mode, which is a way that they conserve power and stop communicating when they think something's going wrong. one of the things that can go wrong is a big storm, then they're instructed to turn off. Other things that can go wrong are just things that go wrong with satellites, like a reaction wheel breaks or solar panel shorts out or something like that. But satellites all have to be designed to have a safe mode, so they have a way to pull back all their power and wait for further commands, perhaps their turn, so they face the sun better or something like that, before they will allow themselves to turn back on again. And so and the really great thing about coronal mass ejections and things coming off the sun is they're physical particles that are leaving the sun, so they're going much slower than the speed of light. So we get the information that something's going to happen really fast from seeing the light signals, but then you have time to warn the astronauts to go inside the space station and stop doing extravehicular activities or whatever, because the particles take a while to get there, and the particles are the things that can really damage the astronauts and other living creatures.
Exactly. Yeah. Thank you so much.
We have a few more questions in the chat, and then we do need to move to our little goodbye survey. So if any of our folks want to help answer those.
Okay, yeah, the aurora is not actually changing the density of the ionosphere. It's all of the charged particles coming from the sun that are interacting with the atoms and molecules in the upper atmosphere and exciting them, which makes the atmosphere puff up. So
Thank you so much.
yeah, so that's what
Appreciate
happens.
that.
So that's why the density of the ionosphere changes and the atmosphere raises up so that it's now dragging on the satellites that were in low Earth orbit.
Thank you.
But I think we still have to save time for our exit questions, right? So, but this has been a fascinating discussion, and thank you so much, Laura, for the wonderful slides and explanations.
Thank you all for having me. I love being here. Like I said, I'm an ADHDer. I can info dump on this stuff all day long.